Good morning, dear colleagues. I'm pleased to present you our research on adaptive windowed synphase analysis of ECG analysis as periodically correlated random processes. In today's anthropocentric world, the quality of human life and timely diagnostics are becoming essential. Among us, the electrocardiogram signal represents one of the most fundamental biosignals in cardiovascular diagnostics. Yet their analysis presents significant challenges due to their inherently non-stationary nature and complex morphological variability. Facing a wave of evolving challenges such as early diagnostic, telemedicine, and remote patient monitoring, computational inefficiency, novel informative feature extraction, ECG become one of the most critical biomarkers. ECG analysis was evolved through key breakthroughs, from the Pan-Tompkins algorithm to QRS complexes detection to wavelet transforms for noise reducing, and empirical mode decomposition for non-stationary signal analysis. Today, deep learning models like convolutional neural networks are pushing boundaries in arrhythmia, classification, reshaping cardiac diagnostics, and so on. Periodically correlated random processes, PCRPs, in terms of energy theory of stochastic signal, ETSS, introduced by Professor Yaroslav Petrovich Dragan and developed by many other scientists and their pupils as Yavorsky, Lupenko, Khvostivsky, and many others, are models of stochastic oscillation with periodic changes in probabilistic characteristics as a subclass of P-class. By definition, cyclostationary processes are not periodic, but their statistical functions, such as mean or autocorrelation, are periodic functions in time. An essential property of the class of PCRPs is what the main task of evolving their characteristics can be solved by reducing them to statistics of stationary random processes with a sufficiently developed. An essential property of ETSS theory is allows us to treat the periodically correlated random processes as a set of stationary components modulated by periodic functions. This approach allows us to reduce the analysis on a non-stationary process to the analysis of stationary one. It's a key concept of an energetic theory of stochastic signal, which open the way to the application of classical method for estimating probabilistic characteristics, and so on. In this context, H ergodicity means the possibility of replacing ensemble averaging with a time averaging, providing the criteria for fast decay of correlation. For example, Slutsky criteria are met. The classical synphase method assumes the samples selected over the correlation period forms vector stationary sequences, and what the autocorrelation period remains constant. However, this assumption may not hold the cardiac signals, which often exhibit stochastic and non-stationary behavior. Keeping in mind its limitation, further improvements such as function of rhythm variation introduced by Sergei Anatolyevich Lupenko, filling the gap between classical synphase method and real nature of human heart. As a result, existing approaches being resource intensive, requiring a priori data, fiducial point detection, and large data set, is focused on template matching and morphological analysis techniques, but these typically require predefined templates or training data, limiting their adaptability to individual patient characteristics and pathological variations. So we introduced our novel approaches called adaptive windowed synphase ECG analysis method. The key feature of our research lie in the adaptability of our approach. At the first stage, we perform a construction of a rhythm function At the stage number 2, we perform identification of segments where the variation of the correlation period is less than 5%. Next stage is applying of window-width synphase method. Next one is determination of mathematical expectation. We call it reference realization, so-called reference realization. And last one is a calculation of a similarity metric between reference realization. It's our key concept of modification of the classical synphase method. So what you see in figure 1 is the input the trended ECG signal sourced from the PhysioNet open database. The peaks have been detected and marked just for reference. At the stage number 1 of our proposed approach, we construct the rate function which reflects the dependence of cycle duration on the cycle number. At the stage number 2, we identify segments where the variation of correlation period is less than 5%. For each iteration, we shift the window one by cycle, capture the ensemble of realization, and derive the mathematical expectation. So we called it reference realization. It's highlighted by red. By combining this reference iteration to previous iteration using proposed by us so-called shape ratio, what can be calculated by derive the root mean square error by mean average error, we generate a similarity metric which capture subtle changes in cardiac dynamics. Slide number 13 represents key aspects of our framework. Thank you for your attention.